All right. We're going to focus more on the whole motion of these objects. We kind of talked about tangent lines, second derivatives for concavity, horizontal tangents, vertical tangents, stuff like that last class. We're going to focus more on, position, velocity, acceleration, because these are, things that are moving over time. Okay? So speed, another thing that we're going to talk about. Okay, when something's at rest, all these sorts of questions. We will get to distance next class, okay, and arc length. Okay, so I'm going to look at the parametric equations. X of t is 5 minus 3t, and y of t is t squared minus 3t. I'm going to zoom in at this location, okay, when t equals 2. And we know that we can find x prime of t, which is just -3, and then y prime of t, which is going to be 2t, but if we look at it at 2, y prime of 2, which is 4. Okay? Well, if I zoom in at that location, what we will be able to see is that this particle, which is moving from the bottom left towards the, or bottom right to the upper left, has this direction that you can use arrows to denote, but in reality, it's moving at an x, distance over time and a y distance over time. Okay, this is dx dt at t equals 2, which is -3, and this is dy dt at t equals 2, which is 4. Okay. Well, if you add those two vectors together, what you will get is this third vector here, which is tough to do. Which is your velocity vector. It shows you that you are going left and up, but it's giving you a direction, and it's going to give you a magnitude. So we'll say this is v of t. It's not x prime, it's not y prime, it's the combination of the two. Okay? Now you'll find that v of t is going to be on the same line as dy dx. However, the magnitude is a little bit different. The speed at which we're traveling is going to be a little bit different. Okay? But this is the same line as dy dx, and all of a sudden we are looking at vectors. Okay, vectors that we've done in physics, and we're not going to go too much into them. It's mostly just this, that we're going to combine a x vector with a y vector to get a vector with a direction and a magnitude. Okay? Okay, so we can use vector notation for all of these things. Okay? We'll start with position. We have been writing position as an x of t and a y of t. We can consider this vectors for position. It's really location, but you can say it's like a displacement from an origin. Other notation for vectors are these brackets that are straight lines. Okay? Now, velocity will have an x component and a y component. Combined, it'll give us our direction and our magnitude. So we can say it is x prime and y prime, because we know if I take a position's derivative, if a position function I take the derivative, I will get its velocity. Well, so that can be listed as x prime, or v sub x of t and v sub y of t. And we know if we take the second derivative of a position function, we get the acceleration, or it's the derivative of velocity. So acceleration could be listed as x double prime of t, y double prime of t, or a sub x, it'll have an x component and a y component. combined, you will be given a direction and a magnitude, which will give you your speed and the direction in which that speed is traveling. Okay. Now, if we go to page 4 of our notes, we'll have a first example where we see this notation, this vector notation, and they're asking you that given a position vector, find the velocity vector at t equals 2. It is super straightforward. This is number 2 on page 4. All you need to do is take the derivative of your position vector, x and y, and plug in 2. And either put it in vector notation or put it in parentheses. It doesn't matter. Okay, so let's go ahead and do that. And I went a little bit more in depth. You know, I would have just looked at this, taken the derivative, plugged into, boom, that's my velocity's direction at time equals 2 for my x direction. This is my and velocity, it's the x direction and magnitude, it's the y direction magnitude. This immediately is telling me I am going up and to the right at this rate in the x direction and at this rate in the y direction. Okay, questions about this? It's very straightforward. Okay, so we also could be given a position, an x equals and a y equals, and asked to find an acceleration vector. Let's go ahead and do that. Number 3. Well, acceleration vectors will have an x component and a y component if we're talking about these 2 dimensions in the xy plane. So you just have to take the second derivative of x and the second derivative of y and plug in 1. You're not going to divide the 2, do anything like that. It's just showing you your y component and your x component. And we say this is a at 1. Okay, just like the previous one, I would say is v of 2. Okay, it's the overall velocity of my particle at the second. Okay, it has the x component and the y component, but this is our overall velocity, two-dimensional velocity. Okay, and this would be the overall acceleration, two-dimensional acceleration. Okay, very straightforward, right? Nod your heads. Good. Now, we might be given a velocity vector and be asked to find a specific position of a particle. Okay, so this starts if I'm given, dx dt equals something, and I'm given dy dt is equal to something. So let's say dx dt is 2t, dy dt is, let's go with 3t squared minus 2. Okay. I'm telling you that my initial position when t equals 0, x of t is 3, 1. Okay? And I might ask you to find the position x of 0 is 3, 1 when t is 2. Okay? Want to start with this example so that we know what we're talking about, where we're going. We need to recall the application of the fundamental theorem of calculus, which says if you have an unknown value that you wish to find, some function value that's unknown, this is equal to some known value plus the change in the function between a and b, which is the same thing as the area under the derivative of the function on that interval. Now this is going to be used if our antiderivative is not easily found. Or if you have a calculator. Okay? For these examples, we could do this without a calculator. Okay? Why? Because I can express my x position as the antiderivative of this plus some c value. And then I could find the c value using my initial condition. I could do the same thing for the other one. Okay, so there's going to be two ways to tackle these problems. Let me walk you through the first way, using antiderivatives. Trying to find my position when t equals 2. Well, I know my x of t will be t squared plus c. Why? I took the antiderivative of my dx dt and my 2t. I know my y of t is going to be t cubed minus 2t plus c. Now I'm going to use, let's move this down. T equals 0, giving me the 0.31 to find my c's. So that means x of 0 is going to give me 3. That's going to be that c. Y of 0, that's going to be 1. That's going to give me that c. And all of a sudden I have my position functions, which I can use to find my position at any time. Okay, x of 2 is 7. Y of 2 is 8 minus 2 times 2 is 4. So 4 plus 1 is 5. Does that make sense? Just take the antiderivative, include your plus c, find your c, get your position function, and you're good to go. Okay? So you took the antiderivative of dx dt equals 2t, and the antiderivative of dy dt equals 3t squared minus 2. Okay? Sometimes that'll be quick. Probably the quickest way is if we have our calculators, we could use them. So get your calculators out. And of course, you could find these with the fundamental theorem of calculus. However, it's really not as quick as if you just take the antiderivative. So I'm going to use the f of b is equal to f of a plus integral from a to b of f prime. Okay, so I can say I have t equals 0 is the point 31. I'm trying to find the position at t equals 2. I want to find x of 2. I will use x of 0 plus the integral from 0 to 2 under f prime, in this case would be x prime, which is 2t. Giving me x of 2 is equal to x of 0, my x coordinate at 0 is 3, 0 to 2 of 2t dt. Plug that into your calculator. Or if you wanted to, you could evaluate this using the fundamental theorem of calculus, but essentially what we did with the antiderivative technique. And we get, boom, our position that way. X of 2 is 7. And we could do the same thing for my y's. I want to find y of 2. I'll use y of 0, which I know, plus the integral from 0 to 2 under y prime, which is 3t squared minus 2. Y of 0, I was told, was 1. That's my y. So I do 1 plus the integral from 0 to 2 of 3t squared minus 2 dt. Plug that into your calculator. You should confirm that that is 5. Okay? Not necessary to do this in your calculator, but if you're given your calculator, it might be the quickest way to do it. You will be given functions whose dx dt, and you'll be given dx dt and dy dt that are not able to be anti-derived. You won't be able to take the antiderivative. You won't be able to find c. So this would be the only way to use this application of the fundamental theorem of calculus. Okay, and if you remember, this just comes from the integral from a to b under f prime is the change in its antiderivative. Such an important rule, they called it the fundamental theorem of calculus. Okay, go ahead and do this example number 4, page 4, number 6. You do it either way. We will do some free response problems where only one way is possible. Pretend you don't have your calculator. Check your answers with a neighbor. I don't know. We'll find out. Try doing it without your calculator to check, and then boom. Error's not right. Okay, denote it by position somehow. That way you know it's a position vector, not a velocity vector, not an acceleration vector. I did it doing a plus C method. Let's say I didn't have my calculator. Boom. You can do it this method. You need to be ready for both. If I had my calculator, I would easily do the application of the fundamental theorem of calculus. All right, next. When a particle is at rest, not just when dx dt is 0. It's not just when dy dt is 0. For a particle to be at rest in two dimensions, it can't be moving up or down or left or right at the same time. So you need dx dt or x prime or v sub x to equal 0 and dy dt or y prime or v sub y has to equal 0 at the same time. If they're both not 0, then the particle is not truly at rest if we're moving in two dimensions, okay? Because we can be moving up or down, but not left and right, and you're moving. You could be moving left and right, but not up or down, and you're moving. You got to be stationary in both directions. Okay, so page 4, number 8. When is the particle at rest? only at the third second or whatever. Not at the negative second or the first second. Only when time is 3. Is both x prime or v sub x and y prime or v sub y equal to 0. Okay? Finally, we'll talk about the speed of a particle. How fast are we moving in a particular direction? Okay? We have our x velocity, my y velocity, and we have this v. This has a magnitude and a direction. The speed is just the magnitude of this guy. What does the magnitude mean? Good question. We said this was -3, right? And this ended up being 4. What would be the number that I would put for v here? 5. Where'd you get 5 from? So what are you calculating? Right, it's the length of your velocity vector. Okay, this was our v sub x, this is our v sub y. We have numbers associated with v sub x and v sub y. I could take the v sub y, and after I ungroup it, slide it over here, and we will create a right triangle, okay, where the v sub x will equal the square root of, the v sub t will equal the square root of v sub x squared plus v sub y squared. Because we'll have the Pythagorean theorem to work for, because we have a right triangle. V sub x squared plus v sub y squared is equal to v sub t squared. Spelled magnitude wrong. Okay. We will use this symbol for the magnitude of velocity. Two kind of absolute values next to each other. Gosh, it's so messy when I write up on the board. I don't know why I felt like writing up on the board there. So given that v sub x squared plus v sub y squared is equal to v sub t squared, using the Pythagorean theorem, you could get that v sub t will be the square root of vx squared plus vy squared. And of course, you can replace that with dx dt, replace that with dy dt, replace that with x prime, y prime, whatever. Okay, page 6, number 11, A. Position of the particle at any time t is greater than or equal to 0 is given by this, and this is a 2/3 t cubed. They literally ask you the magnitude of the velocity vector. Most likely, and we will see when we get to our free response problems, they will say find the speed of the particle at time t equals 5. Okay, so be prepared for just being asked for speed. We need to find x prime at 5, y prime at 5. Use those two values to find, v sub t, or v of 5. The speed at time 5, not v sub 5. The speed, the velocity is going to have a x component and a y component. The speed will just be speed at time 5 equals. Sorry, I should be doing this here. You should have the magnitude of my velocity. Fix that on your guys. And fix that here. Root 2,600. All right, let's finish off with start on our homework on our free response. This was last year's BC number 2 problem. Okay, so last year's BC students had this exact problem. Let's do part A. Find the position of the particle at time t equals 3. This is a perfect one to do because you will have a calculator. You can use a calculator for pretty much all of these problems. These are usually problem number 2 on the BC test. You can't take the antiderivative of dx dt. So you need to use the application of the fundamental theorem of calculus to find x of 3, which is that x of 3 will equal x of 0 plus the integral from 0 to 3 under x prime. And then you got to do y of 3, which is not hard. How do I get y if 3 was negative a half? But it's a graph. So just look. Like, make sure you understand what they're giving you here. Sometimes they'll give you y prime as a graph. Here they give you y as a graph. How do you find x? You have to use the application of the fundamental theorem of calculus. Okay? Do B. And C, you don't know how to do D yet. But that'll be a very short lesson. So. We got an answer. What'd you get? What do we get? What'd you get, Mr. Anson? What, 05? That's all I got. You got to find dy dt divided by dx dt to find dy dx at t equals 3. What's dy dt? Well, you have the graph of y. dy dt would be the slope of the tangent of y. So it's the slope of this line segment, which is 1/2, yeah. And then divided by dx dt, well, you're given dx dt, so you just plug 3 into this. Make sure you're in radian mode, not degree mode. Okay, what about part C? Find the speed of the particle at time t equals 3. Well, you already have the information you need. You have dy dt at 3. You have dx dt at 3. So your magnitude at 3 will be the square root of 0.5 squared plus 9.956 ... squared. Did anybody do that? What do we get for that? No?
14.385.
Thank you. 14.385, Mr. Johnson. Okay. All right, so you have a couple more AP free response problems, and you also have the rest of the packet, excluding any distance problems. You don't know how to do distance or arc length yet. All right, thank you.